Welcome back. In this lesson, we're going to kind of change our discussion to talk about probability distributions. All right, we spent the last couple of videos looking at individual probability values for specific unique events. Well, now we're going to start looking at a way to establish distributions of probabilities for a range of different values all in one shot. And with that, we'll be able to start applying models, and this will be our step into statistics in the coming chapters. But before we can do that, we need to look at discrete random variables. So that's what we're going to do today. All right, so a random variable, if you remember variables from your algebra class, is basically a rule that associates a number with, some specific relationship, okay? In this case, in our setting, that relationship is an outcome of an experiment. Now, to give you some ideas of some of the types of random variables, I'll cite a couple of pages in the book out of our 9th edition of the DeVore text. All right. Now, the first of our discrete random variables that we're going to deal with has to do with the discrete classification, meaning that there are unique numerical outcomes that can be associated with a particular problem. Now, one of the examples that our book cites is talking about when a student calls a university help desk for technical support. Okay, he or she will either immediately be able to speak to someone, which could be classified as your success, or they'll be placed on hold, which would be classification of failure. And then there would be a probability associated with each of those. Okay, it was one of two outcomes. It was either they got accepted or they were put on hold. Okay, and with that, then our random variable x describes that state. You could describe state, in computer terms as, as kind of a binary operation in which you have, a 0 outcome represents one state, and then a 1 represents another state. Okay, and then, of course, we'd have other states defined along the way as well. So that's kind of what we're looking at being able to do. So I'll throw these up here for you, for those of you with the textbook, to kind of give you some examples of what it is that we're going to be doing. As we go through this, I'll set up some others, so for those of you that don't have the textbook, you'll understand what's going on. But for my students, these are the pages that you're looking at. 96, 97, there's some very good examples of these discrete random variables. And then the next one that we'll get to when we get to it, it has to do with continuous random variables, and that one will happen a couple of videos from now when we get into a more open-ended type of problems that we don't have discrete outcomes, that we can actually have decimal value type of outcomes, and they're handled similarly, but they're also handled differently. So we'll talk about those. All right, so what we're doing in this with these random variables is we're trying to set up for probability distributions. Okay, and so what I've done is we can define a probability distribution, okay, which is sometimes called a probability mass function for our discrete random variable x, is given by something that looks like this. So we write it as a probability of x, okay, and then what that really means is the probability that our random variable, whatever it is, that relationship that we're looking for, okay, is equal to a singular specific value. All right, and this is the part that makes it discrete, this equal sign that's here. Okay, if we start getting into inequalities, greater than or less than, then continuous starts to work. But for an example for us to look at, I pulled an example out of a source in which we're talking about airline reservations. Okay, and we all know that airlines tend to overbook things, but we've never actually kind of looked at the probability. So in our particular airplane, okay, we have 50 seats maximum that for people to sit in. There is no double seating, no child in the lap, those kind of things. Okay, and then we also have 5 standby slots. Because based on statistical averages, usually one or more of the standbys, somebody gets sick, they don't show up. One of these later ones, it starts to come in. So what I've done is I've generated the probability function. Okay, so my random variable x is the number of people that show up for any given flight. Okay, and so the probability of x is this p of x value. So if I look at this, I started out at 45, because if I only have 45 show up, then all 5 of my standbys show up. So anything less than this, then all my standbys get on. And again, they're all about trying to optimize money and optimize seat sales. But for us, we'll kind of take a look at this. I won't read all of the data. You can pause video and kind of see this, but we'll kind of show you some of it. So at 45, when the probability of 45 people showing up for a flight on this plane is taken as 5%. 46, it's 10%. 47, it's 12%. 48, 14%, and so forth and so on. Okay, and then 49, it goes up to 25%, and then 50.17 or 17%. And then, of course, we also have the probabilities of these standbys being able to get on. So if you're the 5th standby, you've got a 1% chance of getting on this flight. Whereas if you're the 1st standby, you get 6%. Okay, so what we're going to do is we're going to define our random variable x as being the number of passengers arriving for a particular flight. Okay, so I could be anywhere from 45 to, this 5th one, I guess you could write that as a 55. Okay, and these would be the probabilities. And so if we could look at what's happening on this, okay, the number of passengers for the flight is a random variable x, and then the probability of x is the probability of x. Okay, now, what a PMF is basically a distribution of all of the possible values. So what I'm doing is I'm plotting x and probability of x. Okay, now, we could actually go on and we could write, do our first standby, which is, 0.06%, so that'd be a little guy here, and then it gets continuously smaller as we start to kind of work on those. All right. So we have we can continue our plot, if you will, accordingly. And so what happens is I can draw a line here that represents everything to the left of this is the people that can get on the plane, and everything above this represents the probability of not getting everybody on the plane. Okay, this is what we call a probability mass function. All right, and we call it a mass function because we have distinct setups of values. Okay, and so this point here is associated with 45, this one is associated with 46, and so all I did is I plotted the data that we had. Now notice that there is no such thing as 45.5 or 46.2. That's what makes this discrete, that it's unique, individual, lumped values that make up our probabilities, if you will. All right, so that's kind of what we're looking at as a probability distribution function. Before we were looking at a singular event, the probability that x is 45 and rules for coming up with that using our combinations and our permutations. But now we're looking at all of the values possible, okay, and we'll start doing some things with this. And this becomes the beginnings of being able to make predictive models using statistics. And that's the whole point of what it is that we're trying to do. All right. Okay, so for our data that we had, let's go through and let's look at a couple sample problems that we have here. Okay, first one is what's the probability that all are on board? And that is that, so defining all on board means that I have less than 50 people show up, okay, because basically that's how we start to determine a full flight. So the probability that x is less than 50, again, x is the number of passengers that are non-standby that are on board, okay, and so the way that we do that is we look at our values. Slide this up a little bit so you can see both again. Okay, all we're doing is looking at the probability that x is less than 50. So it's all the values of x that satisfy this requirement. And so for us, what we'll do is say that the probability of x less than 50 is the same as 50 plus 49 plus 48 plus 47 plus 46 plus 45. So it's just simply a summation, if you will, for this piece. So all I've done is I've plugged in the values that came out of these data points. Here's the 50, 49, so forth. And if I add those up, the probability that all the people are on board from a given flight, that the 50 that had seats reserved that were not standby is only 83%. And so this is the place where airlines are trying to capitalize on the money. Because I got 17% more. So if only 83% of the time the plane is fully loaded, well then that's 17% of seats, additional seats that I could sell, just to make up that money. Maybe there's a refund or something costs somebody to not make the flight, whatever the case may be. So that's kind of how we start to do that. Okay, we can go look at the next one then, the probability that they're not all on board. So if you look, here's our not. Okay, so that becomes our complement, and so probability of x greater than 50, and then it's basically all of the probabilities associated with the standby numbers. You can see that adds up to 0.17. Okay, and so those two numbers together end up being the 1.0, which is 100%. Okay, but there's another way I could do this. We could recognize that probability not all on board is the complement of the one that we found before. And so probability of x greater than 50. Now notice this one was less than or equal. There is no equal on this one, so it's greater than 50 distinctly. So this is the same as x greater than or equal to 51, if you will, which is the probability of our sample space, or 1.0, minus the complement of this guy, which is the number we found, and so that's 0.17. And you see that the numbers match up for that one. Okay, now we can start looking at, well, what's the probability that the first standby gets on board? So the only way he shows up, or she, shows up on the plane or is able to get a seat is if only 49 or less people show up for the flight. Okay, and so this one, so again, the hard part of this is kind of deciphering what the wording is trying to tell you. So now we're looking at the probability that x is less than or equal to 49. Okay, well that could be the same thing. There are lots of ways to calculate this, but I could go in the probability that x is less than or equal to 50 was a number we already had, and then I could subtract off the probability of x equal to 50, and what happens is this now turns into the probability that x is less than or equal to 49. That's one of the discrete operators that we're dealing with. So you see how I did it? I subtracted off the 50 to take away the inclusiveness of the 50 here, and then this thing turns into x less than or equal to 49. Okay, and so I could take my number 0.83 and then x equal to 50 specifically is 0.17. That gets me to 0.66. Okay, or we could do it the old-fashioned way, the way that we did it, brute force. 45 plus 46 plus 47 plus 48 plus 49. I add all the numbers and I do indeed get that same probability back. All right, so there's lots of ways to do this. Now, like I say, for a few numbers, that second method is pretty convenient, but in reality, if I can do something like this is generally a lot easier because I can subtract off one piece or subtract off several pieces, and I can keep this line of equations from getting very, very, very long. Okay. Now, again, we haven't talked about how you calculate the actual probabilities yet, and so there will be some models that we'll get into in the coming videos. Okay, on this, I gave you the probability in the example, but one of the things that we'll start learning how to do is how do we predict these percentages themselves. That's the second step in all of this. Okay, and then just for good measure, the probability that the third standby is on board or is able to get a seat would be then the probability that x is less than 47. So 47 original people can arrive at the most. And then so this one's easy enough. I'll just do 46 plus 46 plus 47, 0.27. So no major issues there. Okay, so yeah. All right, now we should probably talk a little bit about some of the notation that we have. Okay, and so we've got the probability that x is equal to x. We're going to define x as my random variable again, and then this little scripted x is a kind of an integer value. So again, we're looking for specific values in my random variable equal to certain numerical values. Okay, all right. So the way that we write this is I'm going to write this, and we kind of write it as kind of an algebraic notation. Functions of x is equal to the probability of some numerical value of x greater than or equal to 0. So it has to be positive values. That's one of our first axioms. You cannot have a negative probability. Okay, and if I sum up all of the x values of my probability function, I should get 1.0. That's the same thing as saying it's the probability of the sample space. So these two properties never change. Okay, now, some probability mass functions may include, a parameter in their definition, such as, maybe it's the probability of x given some parameter of alpha, in which for a value of x equal to 0, I get this probability. Okay, and then for an x equal 1, I get the complement. So you see 1 minus alpha and alpha, those are complements that added together, these still add up to 1.0, so it's a complete function. Okay, this is called a probability mass function, okay, and which is a binomial situation. And so we can have, this one will set up, yes, no, true, false, blue, not blue, right, not right, so forth and so on. Cases where you have two distinct values, this could actually start to become pretty powerful, and we'll start to work on this. All right, and so what happens is this orientation here, you start to see a form start to establish, and we talked about this in the last exercise when we were dealing with our sequences of successes and failures in our binomial operation. Okay, and you start seeing patterns that look like, well, if probability p, this lower p, is a probability of an event happening, then 1 minus p is the probability the event doesn't happen, and then I can raise that to some x minus 1 power and then multiply that by some probability. Okay, and all of a sudden I get the knots multiplied by our probability of the not knots, or the wills. Okay, x equals 1, 2, and 3, and so this form starts to become very, very common. Okay, and you'll see that coming up, because all it is that at the end of the day, this is all a combinations or a permutation problem, and then we'll add some things out on the front of this thing that will help us put strings together. But keep your eyes open for this, and I'll point it out as we come along for the next couple of times. All right, and you'll start to see that. So this is a very common construction form, if you will, for calculating this probability. Okay, all right, so that's our probability distribution function. There's another one that's related to this that kind of helps with our calculations, But the scenario where we're looking for to add up, all of our values less than or equal to some value. So this one, before we were playing with an equal sign. Now I'm doing x less than some value. So this includes all the values of x less than that guy. All right, and so we're going to write this as a CDF, okay, which stands for cumulative distribution function. And the nomenclature is usually that CDFs are written with capital letters so that you can distinguish them between the probability density functions, the lowercase f that we saw. And so all I'm doing when I do this, I'm summing all of the y's that are less than my particular value of x of the probability of those values. So in the case of our airline passengers, if I wanted, probability that x is less than or equal to 46, this is the probability of x equals 0 plus probability of x equals 1 plus all the way out to the probability of x less than or equal to 46. And I would sum up all of these things. And a lot of times in these CDFs, they'll set up some tables that will help you to speed up the looking at process, because that's kind of a lengthy calculation. But if I have an equation model that lets me predict every one of these individually, then I can tabularize these, and all of a sudden I have a great tool for being able to speed up the process for a problem that is looking to do probability of x less than or equal to 46. All right, so that's kind of where we're going with this. All right, so let's try one, kind of a small one to kind of get ourselves going here. All right. Let's see. See if maybe that helps us a little bit. All right, so let's try one. So we have our probability function x is equal to 0.5 when x is 0, 0.167 when x is 1, and 0.33 when x equals 2, and 0 at all other values of x. Okay, this becomes important because that fully defines my sample space. So I've drawn this graph. It's pretty simple. I have a 0, a 1, and a 2, and their corresponding probabilities. And I use a little f here because that's my probability distribution function. All right, so to turn this into a cumulative distribution function, all I do is I write down all my values of x, 0, 1, 2, and then any values of 3. We're assuming all positive numbers on this. Okay, and so to get the cumulative for x equals 0, I sum up all the values up to 0 of my original. So that's just the 0.5. Got it. To get the cumulative for x equal to 1, I add up all the values up to and including that value. So now I'm going to take 0.5 and 0.167, and that's what I've done, and so forth and so on. And then to get to x equals 2, I add up all the 2 before it. And again, we're doing less than or equal. Okay, this is x less than or equal to some value of x. So that less than, I have to include the value that I'm looking at. All right, and then 0.5, 0.167, 0.3, and plus 0 gets me to the last guy. All right, and when I do that, okay, we start to get and I simplify my math, my cumulative distribution function is then for x less than 0, it's a 0 value. For x equal to 0 exactly, it's 0.5. For x equal to 1, 0.667. X equal to 2, 1.0. X equal to 2 or greater than 3, it's 1.0. And you can see that what happens is in a cumulative, it accumulates, hence the name, all of my values for a specific item. So now I can, with these CDFs, I can go in and say, well, what's the probability that x is less than or equal to 1? And I would know that x less than or equal to 1 is 0.667, and that comprised of the 0 value and the 1 value added together from our original function. So this becomes pretty easy. Some things that you'll notice is that you'll notice that this thing increases up to 1.0 and then it never goes above. All right, because this line represents the probability of our sample space. Okay, I can't ever exceed that value. But I could go all the way out to 1,000,000 on x and it's still that same cumulative value. Okay, so some interesting things happen. Again, this is kind of just a basic example. It's not real interesting, but it kind of shows you how to put the CDFs together, hopefully in a logical sense. Okay, so what it does is, again, this allows you to answer those less than questions. Remember, we're always looking for keywords, and so a less than, if you see a less than, your mind should be thinking, hey, can I do this with a cumulative? Okay, and so the notation in your book that you'll see and the way that's written in other sources is that capital F of 1 is the same as probability of my random variable x being less than or equal to 1 equal to 0.667. And we should be good to go on that. All right, okay, so for any two numbers a and b with a less than or equal to b, there's some things that we can do. Okay, so we're going to come up with some mathematical relationships. Maybe I want the probability between two values. Okay, and so maybe I do a less than or equal to x, less than or equal to b. Well, we know less than or equal to b, that's the cumulative of b, and then minus, okay, the function of a and then we put a negative sign on this where the a negative represents the largest possible x that is strictly less than a. Okay, and so again, all we're doing is we're adding up all of the cumulative stuff to get me the first one minus all of the cumulative stuff to get me the second. Okay, so then the probability of a specific value of x equal to a, this is basically taking my CDF and flipping it back into a PDF, because now this is x equal to a specific value of a, if you will. Okay, that all I do is I add up everything less than a, okay, and I subtract it from the cumulative at a, and that will get me my PDF. So I can go back and forth between these. Now, again, we don't do this a whole lot in practice, but the ability to be able to do it is pretty handy. Okay, all right, so let's try one real quick. Okay, and so what I've written is I've written a cumulative on here, and here are all my probabilities: 0, 0.6, 1.19, 0.39, 0.67, so forth. You can read through all of those, and then I have discrete values set up for x less than 0. Okay, whoops, that should be a 0 there. Okay, 0 less than or equal to x less than 1, 1 less than or equal to x less than 2, and you'll notice the less than or equal to on the left side, there isn't one on the other, so the inclusive shows up. Now if I plot this CDF, you get a picture similar to what we saw before. So you can see how it kind of builds up, and then we get up to this 1.0 value up here, and then it caps out at 1, and it's 1.0 everywhere else. And so all I've done is I've plotted values of x. Okay, so these totals are summative, if you will. That's what makes it a CDF. So again, I'm plotting CDF, so capital F there. Okay, all right, now to find the probability that x is equal to 2 on this, what we're looking at, again, this is a CDF, so the probability of x equals to 2 is actually, for 2, it's this height. That's the probability of 2, if we start to look at that. Okay, so the probability of x is exactly 2, okay, and so CDFs don't handle the exactly case very well. Okay, so if I write this, all that last function, that a negative stuff that you saw, all it's saying is that the probability of x equal to 2 is the probability that x is less than or equal to minus the probability of x less than or equal to 1. What this really was x less than 2, right? But because we're looking at distinct values, the only distinct value, the first distinct value less than 2 is x less than or equal to 1. And so that will get you the height of that step. And so this guy becomes F2, x less than or equal to 2, and this guy is written as F1. You have to get it into a less than or equal form. That's the trick in all of this, right? So for our table on this, then, I'm going to take the x equal to 2 case of 0.39, and I'm going to subtract off 0.19, which is the x greater than or equal to 1, or sorry, less than or equal to 1 case. Okay, so that includes the x equals 1 scenario. And when I do that, you can see that the probability of x being specifically equal to 2 is 0.2. Okay, now let's try probability of x greater than 3. Okay, so again, everything that we do with the CDF has to be into the form like this. So x greater than 3 is the same as 1 minus the probability of x less than 3. So this becomes 1 minus the functional value of 3 for the CDF. All right, and then we can plug those in the same way. So 1 minus 0.67 gets me 0.33. So that's the trick, if you notice on all this thing, is that I can't handle this one with the CDF, but I most definitely can handle this one. And so this complement becomes very, very powerful when dealing with CDFs, that I can flip my inequalities. And if I'm greater than a number here, I'm less than or equal to that same number subtracted from 1 there. And so that's the game that we're playing. All right, so if we look at this now, probability of 2 less than or equal to x less than or equal to 5 is the same as the probability of x less than or equal to 5 minus then the probability of x less than 2. And again, I don't put an equal sign on this because I'm including x equals 2 in the calculation. So you gotta watch those inequalities and those equal signs on here. So that's going to include x equal to 2 in our calculation. So 0.97 minus 0.19 is equal to 0.78, and that's all we're doing is we're setting this piece up. Okay, all right, now let's try a little bit of a harder one. How about probability of 2 less than x less than 5? All right, well again, I got to get it into a less than or equal set. So here I'm not including 2 in this, so the next integer above 2 is 3. So that 3 changes the less than to a less than or equal to. Okay, and then x less than 5, okay, doesn't include the value 5, so this is x less than or equal to 4. All right, so this is the heart of what we're doing. So you got to kind of be able to write these expressions, and that's a mandatory skill going forward, is to be able to understand the difference between these inequalities, and that's one of the things that you're looking at. So the probability of x less than or equal to 4 minus the probability of x less than 3, okay, gets me to that case, and so that should be a less than a non-inclusive 3 value, right? Because I want to be able to capture the 2, so that's 0.92 minus 0.39 gets me 0.53. So that's how you write the probability of 2 less than x less than 5, is you have to write it again in a form that looks like that. That's the challenge. Okay? All right. So I know that was kind of a whirlwind tour of basic random variables and probability distribution functions and cumulatives, but these become basic building blocks for everything that we're going to do going forward. Okay, they're very, very important to be able to get these squared away and to understand these basics, because we're going to come back to these basic skills time and time again. Notice everything we've done has followed all of the basic properties of probability as we defined them earlier, but this particular set of skills, being able to move back and forth on these graphs, is critical to what we're trying to do. So, okay, I think we'll stop there. We'll pick up with some more examples later on in the coming videos, and we'll get into specific probability distributions as we start to move forward in the series. So, thank you for your time. As always, if you like the video, leave us some comments down below, and be sure to subscribe to the channel. We would greatly appreciate it, and we will see you next time. Thanks. Hope all is well. Happy engineering.